Hi, good morning everyone. I'm Nick Martin, an engineer here at Markforged, and I'm joined by...
My name is Michelle, a product manager here at Markforged.
And so today we're going to be talking about our sintering furnace. So we've talked a bit about metal the past few weeks in our live stream, and if you've tuned in, you know that our metal process includes a sintering furnace at the end of the process. And so Michelle is our resident expert on all things metal, and so that's why I brought her on today, so that she can teach us a few things about sintering in general and about our sintering furnace. So I think we'll just start off. For people out there who don't have really a technical understanding of what sintering is, it's not a process we invented. It's existed
It's been around for a long time.
For a very long time, for literally thousands of years. If you've ever fired clay before, that's a very similar process to what we're talking about, except we're specifically talking about metal powder fabrication. Yeah. And so the sintering process is a little different in that, and if you want to quickly walk through what sort of process we go through in the general metal powder sintering process.
Sure. So a lot like firing clay, you take your metal powders, or for clay you just have basically dirt, you encapsulate it in a polymer material, and then basically you're trying to burn off all of this polymer after you've made the shape you wanted. For us it's 3D printing. For people working with clay, it's molding it with their hands. When you put it into a very hot furnace, you basically burn off the polymers and you're giving energy to these powders, whether they're clay, metal, ceramic, whatever this material is, giving enough energy to go from being powders to being a solid part. So there's a energy driving here, kind of driven by thermodynamics, the fancy word, but basically you give it heat and you're taking powders and making a bulk solid part.
Cool, yeah, so really that idea of taking this object that's really, in the case of metal, it's a really brittle object, and giving it heat and turning it into that solid metal product.
So we
at
got
the end.
a couple of examples here. So this is a printed metal part before firing, and afterwards you see it's shrunk. We've removed a lot of the plastic, and we've actually taken the powders and reduced all that space that was the polymers had filled, and made a basically 100% dense part.
Cool. All right, I'm excited to dive in. Also, by the way, if you have questions or comments throughout the live cast, throughout the stream, feel free to just ask us and we'll answer them as appropriate throughout it. So just throw your questions in the comments whenever you like. So let's backtrack a little bit. Why is sintering an important process in general? So why is sintering for metal fabrication a thing?
So there's some geometries you can't really make without with traditional manufacturing methods. So sintering is one way you can get around that. There's also some metal materials that are just very hard to work with. So sintering, there's a couple other processes besides 3D printing to make your preform before you sinter. So there's press and sintering. So people take powder and just literally press it together to the shape they want. Or there's metal injection molding. Yeah, like a sandcastle basically. Or there's metal injection molding where you're taking basically a similar idea where you're taking polymers and metal powder, pushing it through injection molder and making your final form before firing.
Okay, cool. And in terms of if we're talking about metals like titanium, where it's extremely hard to machine and work with, it's a really good process for that, because sintering titanium is not orders of magnitude harder than sintering steel. Whereas if you're going to sinter or if you're going to machine a steel, it's easier than if you're trying to machine or titanium.
Right, exactly.
Cool. So also another advantage of sintering is that you can, if done correctly, you can achieve pretty high levels of purity in your part.
Yeah, definitely.
Yeah. Cool. So in terms of sintering for metal processes, they fall into two camps. We have laser sintering, which is like DMLS processes that you may have heard of. We've talked about it on the show a couple times. And then there's furnace sintering, which, as Michelle mentioned, is like MIM furnaces, or our furnace, for example, is also a sintering furnace. And so on the laser side, a DMLS process, for example, you have a machine that lays a layer of powder and then zaps that powder in specific points to sinter the powders together. And then lays another layer and then sinters the powder together until you get that 3D shape that you want. That process can introduce internal stresses into that part because the part cools and heats at different rates as you're zapping it with that laser. And so that's one thing, as we talked about last week, getting rid of those internal stresses by heating the part afterward is something that has to happen there. Whereas putting in a sintering furnace, we're talking about heating the part uniformly throughout, which is something that we'll touch on in a little bit. And so, so in terms of furnace sintering, what is actually happening in a furnace while it's sintering parts?
So like you described, instead of having layer by layer heating with the laser method, with our furnace, you take your part, which is fully shaped to whatever you want, and we're uniformly heating it up from room temperature up to a sintering temperature. For our process, we actually have two parts to it. The first is a debinding step, in which we get rid of all of the polymers that are holding the powder together. After that, it's kind of like a sandcastle of powder. Then we kind of heat up to a much higher temperature where the metal doesn't exactly melt, but we're getting closer to the melting point so that we're giving the powders enough energy to coalesce and reduce their surface energy. So if you imagine a bunch of powders sitting on top of each other, a lot of circles sitting like this, there's a lot of driving force. If you give it enough heat, it's going to want to come together and reduce all of that surface and become more of a solid part.
So when we're talking about sintering, we're not actually reaching a liquefied metal.
No, sintering is a solid process. You're not actually, if you were to get it hot enough, you could melt it, but then you would lose your shape.
Right. So it's a delicate balance between having it hot enough where it's actually sintering together and not making it a pool of liquid metal.
Exactly. And actually, we do a lot of research and development here to make sure we don't get too hot to get that liquid phase. And if we do, we try not to do that.
Yeah, exactly. And so one thing that you mentioned is heating it uniformly. One important aspect to sintering furnaces is if, like you mentioned, especially ones that have that debinding phase that we're talking about, if the part is not uniformly heated and you have part of the part that's still getting that rest of that binder out, and another part that starts sintering together, you can start getting cracking in the part. Whereas if you have any sort of temperature gradient across the part, is when it introduces those imperfections. And so having that uniform temperature across is really important.
So that's one thing we pay special attention to with our furnace, to make sure that we're uniformly heating. We're going at a rate that makes sure our entire hot zone, where we tell people to put their parts, is uniform, so you don't have any weird distortions coming from one side being hotter than the other.
So what sort of measures are taken in Markforged process specifically to make sure that uniform heating happens throughout the chamber? How do you actually achieve that?
So we do a lot of work to make sure the rates at which we heat up are controlled, so we don't overshoot our temperatures. We have a lot of good electronic controls in there. We've designed our hot zone, our setter plates, to be just big enough for you to put all the parts you want, but small enough that we ensure quality temperature uniformity across that entire volume.
Gotcha. Cool. So we touched on uniform temperature throughout the volume. What are some other important aspects of a sintering furnace? Like what makes a good furnace, I guess I could say.
Right. So for stainless steels especially, what sort of gas you put in there is important. So you want to make sure we don't have an excess of contaminations like moisture, for example. So unlike firing ceramics, where you do want oxygen and you want moisture to make sure you get these nice oxides, we want the opposite in sintering stainless steels. So we want to make sure we keep our composition the same. We don't want to introduce any extra carbons. So that could be coming in from our binders, and we're burning it off. We want to make sure we burn off all of our binder material. We don't want to leave any residues behind. And we also want to make sure that we don't have any moisture in the system, because steels, if you let it sit in water, if you let there be oxygen present, you're going to oxidize the part, and that will make if you have oxidation happening on your powders before they're fully densified, you're going to have really weak properties. So we make sure we have a good clean gas, so like high purity gas, for our whole sintering process.
So you could have parts that oxidize in the furnace that end up still being the correct shape, but their mechanical properties are just off.
Right. So sometimes you can't even tell that it's if it happens, in the run itself, and it recovers partway through, you might not even notice exteriorly that it looks any different. But once you put it into use, it's going to be a little bit worse performing.
That's interesting. So you mentioned that it's sintered in an atmosphere, so there's gases that are being pumped into that furnace. Can you talk a little bit about what those gases actually do in terms of keeping those parts? So one, it's keeping it from getting oxidized, keeping oxygen out of there. What else is the purpose of having it sinter in an atmosphere?
Yeah, so the atmosphere we've chosen is a forming gas, which is basically we've added a little bit of hydrogen to an inert gas. In our case, it's argon. That basically will react with any oxygen in the system, and also just at temperature that we're sintering at, it'll keep that entire environment in a reducing environment. So there's these chemical equilibriums that you can look at for how iron turns into iron oxide or chromium turns to chromium oxide. And with there's certain levels of moisture that'll push you up and above into oxidizing or reducing environments. So adding hydrogen mixture, we're keeping our moisture levels down and operating in a reducing environment. So if there's any sort of oxygen present, we'll get rid of it.
Nice. I told you guys, Michelle's the expert on this. She's the metal person. All right, looks like we got some questions. Using the analogy given of the sandcastle, what were to stop the part literally falling apart during the debinding process? What keeps it together between the stages?
That's a great question. So there's this force called van der Waals. You might have learned about this in high school. Basically, these are weak forces that hold together the parts. And that's why, in this fragile state, you don't want to go jumping up on your furnaces or shaking it. But that's holding the part together at this stage. And once we've kind of burned off all of the binder, we do try to move quickly to reduce that amount of time that is in a weak point. Once you get to a certain temperature, you'll start tacking the powders together, and that starts to lend your part strength. So before you're fully densified into a solid, full solid part, and right after you've burned off all your polymers, there's this short window of the sandcastle state, after which we start to have these small, think of tiny weld tack bonds between your powders. If you've ever welded before, you always tack a couple of points together to kind of hold it in shape before you do your full weld bead.
Cool. That was a good question. Let's see. Sinter 1 and 2 are manually set up for each part produced from Metal X. So I think this question is asking if you're actually programming the sintering oven, and so depending on the metal that you're using, it's the sintering furnace basically automatically sets all that temperature profile and the settings for you. Yeah,
so we spent a lot of time designing our profile to work with our material. So for each new material we've launched, so our H13, for example, has its own sintering cycle. It's optimized for our H13. It's basically, depends on the material is what I'm trying to say.
Yeah, exactly. And so it can be a batch process, right? So Michelle mentioned it has a plate that's about a foot long and then maybe
4.5 inches wide, I think.
Yeah, and 4.5 inches tall for the Sinter 1. Sinter 2 coming to you soon. But you can do batches of parts. Like for example, if I have multiple of these grippers, I can place many of these green parts, and then as long as they're the same material, and they'll go through the same sintering profile, then they're fine. Let's see. Another question. What were to happen if your binders are not completely out before sintering and you sinter the part?
That won't happen with our process, but if we're talking about in general, you'll probably end up with bits of extra carbon in your metal material. For some steels, they're more forgiving about having a little extra carbon in your final chemical composition. So extra carbon could make your steel a little more brittle, or just affect your properties a bit.
Yeah,
we tried not to have that.
Yeah, especially when we're talking about low carbon steels like 316L that we're going to be coming out with pretty soon, a more weldable stainless.
Right.
Trying to keep that carbon low is really important. All right, let's see. We'll answer these next few questions, then we'll continue with what we have prepared. Would sintering in a vacuum be viable to avoid all harmful added gases?
People do sinter in vacuum environments. In fact, some of the large metal injection molding houses have furnaces that run in vacuum. You want to be careful with vacuum. You want to think about what metal you're working with. So for example, with 17.4 in particular, if you pull a vacuum as you hit your sintering temperatures, you might actually vaporize some of the alloying elements in it. For example, at high temperatures, chromium and copper have a low vapor pressure, so you can actually pull that out of your metal and
drop it with 17.4
drop it from 17.4, or you'll end up with a coated chromium on your walls. That's not so great. Yeah, your metal will not be performing as well. So you want to be a little bit careful there with materials, but people do use vacuum for assisting in the debinding, for example. They want to make sure you pull off all your hydrocarbons out. And some people use it to help get a little bit higher density. So.
Cool. That was a great answer. All right, is SLS the best technology for printing on a manufacturing level? Not as relevant to what we're talking about now. So we won't answer that one now. SLS is a really interesting technology, though. That's on the plastic side.
Yeah. The metals, I think, just called SLM.
SLM would be the metal, or actually, well,
SLS is kind of a generic.
Yeah. All right. So, would you catch excess oxidation with an Archimedes float for density checking?
If you've got enough oxides, maybe. I don't really know if you can detect that from just a density check.
Okay.
Possibly.
Possibly. That's our answer. Official answer from Michelle.
Sorry.
No, it's fine.
Usually if it's an oxidized part on
Yeah.
the surface, you can immediately tell it's just not shiny. It's got this dull blackened, or if it's a low temperature oxide, it's kind of yellowish. Depending on when you have these oxygens introduced, you can have various colors of oxide forms.
Yeah.
It kind of depends on how thick that oxide is grown on your surface.
Gotcha.
So if you've seen a nice shiny part, you know the exterior is not oxidated. Yeah.
All right, so we're going to keep going on with what we have planned, and then keep putting questions in there, and we'll revisit questions as we keep going. So, so we talked about like what's important in a good sintering. We talked chamber temperature uniformity,
Yep.
gas mixture, and then in terms of contaminants, we talked over that a little bit: carbon, moisture, oxygen as well.
Mm-hmm.
And then in terms of like the time and the temperature, do you want to touch on that a little bit? How you actually structure how long it sinters and what the temperature gradient kind of looks like.
Right, so we spend the time here to do some research to make sure what time and temperature we should actually be sintering with all of our materials. There's kind of an optimization strategy here of getting the highest density possible, getting the best mechanical properties possible, and the ideal microstructures. So there's always a trade-off between, you can go much higher in temperature, get some more density, but you run the risk of, potentially getting too close to your melting point. So we want to make sure we're consistent all the time there. So what else do we trade off of? We look at our microstructure, so we want to make sure we have the right size grains growing, so that tells you how strong or how ductile your part will be. And
so in terms of you said there's a trade-off between how high you make the temperature and then you're getting close to the melting point.
Right.
Is the trade-off between those advantageous material properties of strength that comes from the density and the part losing shape because it melts, or what's that actual trade-off that's happening?
Yeah, so that trade-off is you don't want to get so close that you start to
You have a puddle.
you have certain overhang geometries will have more of a distortion.
Yeah.
Right. So we want to make sure we still have high enough strength to make sure we're keeping our parts the shape that they should be. Another thing that we take into consideration is oftentimes if you can optimize for strength or ductility. That kind of is like how big do you want to grow these grains. So if you sinter for a very, very long time, you can get these grains which are coming from your powder to basically keep growing and growing and growing. And as the grains grow, you can increase your density, but you're going to start losing out in strength, but gaining in some ductility. So there's kind of a map here of like what should we go for, and we optimize for high strength. So 17.4 material, for example, we try to get the highest strength possible.
So density doesn't necessarily mean strength. It can just
Right.
mean you have more ductility, but you're giving up strength. So then the stronger parts, if you're looking at the stress strain curve, just have a shorter tail, essentially.
Yeah, exactly.
Cool. All right, so we mentioned that the MIM process is similar to our process in that it's a similar material, metal injection molding. You injection mold a part
Right.
using a similar material to us, and then you put it in a MIM furnace.
Right.
How is a MIM furnace different from our furnace?
It's a great question. So MIM furnaces, so the process of metal injection molding usually yields, thousands of parts. And so the furnaces are appropriately sized. They're, size of half a room usually. And the actual design of the furnace is quite different. So they're used to sintering a bunch of very small parts. They have trays and trays of the very identical parts.
Right, specialized for smaller parts.
Specialized for smaller parts, and they're also just much larger. And the designs for a MIM furnace is different from ours. They use a what's called a cold wall system. So basically, in order to increase their effective heat zone and the ability to heat up and cool very, very quickly. Oh, that is showing. Awesome.
There we go.
Here, let me put it on the actual slide. Here, I'm just go really quickly and show. Is that actually showing?
Yeah.
Okay.
Yeah, it is. You're good.
Full presentation mode. Cool. So just backtracking a little bit, here's a diagram of the stages of sintering where we're talking about the powders necking together. Kind of that intermediate stage is where you have just enough strength for your parts to hold together before you move on to densifying, which is that third image there. And here. Cold wall furnaces are typically what MIM furnaces are. So you have a very large hot zone, but you have your heating elements within your in the same area as your parts. So you have insulation on the exterior, then your heating elements, and then your actual parts. So the issues here is you've got to make sure you keep your heating elements clean. So that's why then furnaces typically run a furnace. They want to make sure run a vacuum. They want to make sure their hydrocarbons or whatever they're burning off don't condense onto these coils. So the challenge is keeping that clean. Whereas if you run a hot wall furnace style, which is what we have, you have a retort. So that's basically our parts are inside a refractory tube and our heating elements are outside of that. So we don't have to worry about keeping those clean. We just have all of our parts in this tube. So we can run basically, we end up having smaller parts loading available, but we're able to keep our environment very clean.
So is there any worry about the retort at that very high temperature introducing any impurities into those parts?
Not really. So the retort doesn't have any carbon. So like we run with a carbon-free retort. If there was carbon, if you had some hydrogen in the system, you can make some methane, and methane could then deposit on your parts, and that's not so great. You don't want to have methane.
We try to reduce the methane.
Yeah, exactly. So it's a refractory metal, so that means you don't actually have any reactions with our hydrogen or inert gases. So it should not affect your parts negatively in any way.
Awesome. Cool. Let's see. Yeah, so also you mentioned that so each material has its own special sintering process, basically, right? So you can't just like throw a 17-4 part and a copper part in a furnace and be like, go make metal.
No, you can't do that.
So can you walk through generally like why is that, and what are some like general guidelines, like stainless steels? How do you sinter stainless steels differently than you might sinter like titanium, for example?
Yeah, so for stainless steels, you really want to keep, we introduce some hydrogen to keep the environment very clean and reducing. With titanium, for example, you don't want to introduce hydrogen because titanium will form titanium hydrides. So you run it just straight up inert environment, so it's just like straight up argon. Titanium is a very sensitive metal. It loves carbons, it loves oxygens, it loves hydrogens. It'll react with basically any contamination in your air. So you have to run a very clean environment there. This is where you want to make sure you're running pure gas, inert gas, and just the whole system is clean.
Interesting. So it's interesting that the atmosphere changes very significantly depending on which metal you're actually sintering.
Yeah.
Cool.
It does.
And also, looks like you have a picture of...
Yeah, you could switch back to the screen.
Yeah.
So it's just walking back a little bit. That's a metal injection molding, like MIM style furnace. You can see the scale of that. It usually costs upward of $1 million.
Yeah.
And you can see that there's a lot of design and effort to make that work well consistently.
Yeah.
They've optimized their system for what they need to do.
Right.
Yeah.
So to be clear, they're not putting like giant car-sized parts.
No, they're putting just thousands upon thousands of small parts. Imagine all the little components in your iPhone, for example, or things that are like less than the size of your thumb. Basically, is what metal injection molding parts typically look like.
Yeah, so it's really just a mass production process for metal.
Exactly.
And it's interesting because we talk about keeping the temperature gradient across a part the same, or not having a gradient across the part when you're sintering it. And when you have tiny parts, that's a little less of an issue.
Right.
And so you can have that giant volume that you're putting all those parts in, because having a part that's this small, it's hard to have a temperature gradient across that part.
Right.
Yeah, that's interesting. All right, it looks like we have a lot more questions. Let's backtrack a little bit. Let's see. When is it necessary to use a HIP sinter versus just using a standard vacuum or atmosphere sinter?
Oh, so hipping is usually a post-process method in which for those who don't know, HIP is hot isostatic pressing, often called hipping.
Okay, cool.
Basically, what you do
Shows
there
what I know.
what you do there is you take your part and you take it up to a high temperature, and you then add a huge amount of pressure. So I think like 20,000 psi of atmospheric pressure, and that forces your part to like densify significantly. So as we mentioned, a lot of our parts in atmosphere sintering, we don't achieve 99.99% density on the material, but we achieve a high enough density where you get most, if not all, of the mechanical properties you care about. For some applications, I'm sure people will need that 99.99%. That's where you go to HIP parts.
Got you. And so is hipping something you would do to MIM parts?
Yeah,
as well.
People can do that to MIM parts if they need that extra density. Yeah.
Right. Okay. And then, so with that density, are you seeing an increase in terms of pressurizing it in the sinter, you're seeing an increase in both ductility and strength, just like all your mechanical properties of like a wrought piece of metal?
You get a lot closer to wrought properties, yes. Wouldn't say you're quite there, but you do get most of the way there.
Cool. All right, let's see. What is the highest density of the part, and also compared with SLM? So this actually has a two-part answer. So part number one, Markforged parts, if you've learned a little bit about our metal process, are printed with an infill, and which is partially because the washing process, where the Opteon Scion needs to infiltrate the part to begin that debinding process. If it's printed with an infill, you can retain most of your strength, but spend a lot less time washing the part to debind the part. And so in terms of density of the actual part, that infill makes it so if you take the part as a whole, isn't a fully dense part. But if we look at where there is metal in that part, what sort of densities are we looking at?
So for our 17.4, we're seeing about 96% density if you're just looking at the metal side. Again, if you really need that extra bit of density, you can hip it. Yeah.
Cool. All right, and can I interrupt the sintering process to add more products into the furnace?
No, you can't do that. So with our wash, you can pull it out, put new parts in, keep on going. With the sintering process, once it starts going, you don't really want to stop and pull it out and put new parts in. Like we mentioned, there's going to be a critical period of time in which your parts are lacking the strength the polymer gave it and not quite tacked yet. So if you pull it out, you run the risk of shaking off your parts, distorting it, breaking it. You know, it's very fragile in this state. So it's a batch process. It's very much a batch process.
Yeah, it's different than if you're baking cookies, for example. You put the oven at 350 degrees. You put your cookies in, and you can swap trays in and out as you go because the temperature is just the same the whole time. But sintering, we're talking about a very specific temperature profile that you're adding to the parts that has some specific stages that it's going through. You need to debind, and then you actually need to sinter the part together. And so interrupting it during that will make you have sad parts.
Exactly.
Okay, let's see what's next. How about tolerance and surface roughness after sintering? So tolerance, we get this question a lot. So as with basically anything, any metal process out there right now, it's usually described as near net shape. So giving specific numbers is hard because, as we always say, it's geometry dependent and it's also size dependent. And so giving an actual number is a hard thing to do. One thing we say is if you really need those specific tight tolerances, if you're making tooling, for example, post-machining the walls of the part is something that you can do because what you get is parts that are metal parts out of the furnace, so you can treat them just like any other metal parts. In terms of, what was the second part? Surface roughness.
You'll still see print lines. That's kind of the surface finish you get, but like you just said, we can take that up to a belt sander or a, what do you call those? Sandblasters, and just clean up that surface to get that smooth finish you're looking for.
Yeah, and so I think I saw another question about layer lines somewhere down, now that we're talking about it. Oh yeah, can you see layer lines after sintering or has it vanished? So you can see the layer lines, but an important thing to note is that it's really just like a cosmetic thing. It's not like in plastic printing or our composite printing, for example, where in that Z direction you do have a little less strength because of the Z layer adhesion. Whereas in metal, because it's sintering, you essentially are getting that isotropic strength.
Right. So you've got because of the way the process works, you've got more adhesion between layer than you would if with plastic printing. There's no heating up and then cooling down between layers. It's the whole thing is heated up at one time.
Yeah, exactly. So you can see the layer lines. This is printed. I think this is 125 micron layer height, so you can see them. But it's really it's more of cosmetic than that. It can be polished away.
Definitely.
All right, let's see. What is the difference between the powder and metal X filament versus powder bed laser machine?
Well, our machines take powder and put them in a polymer blend so that we can actually print with it much more safely. So one of the big things is we can actually process our materials without going to a clean room, putting on a full suit, or having to worry about powder, going all across the environment. So that's one big benefit of running our systems. The actual powders themselves are probably different sizes. I don't know what the MLS powder sizes are because they're trying to make sure it's large enough so you don't have inhalation issues as much. They probably have more problems with dealing with finer powders.
Right, but when we're talking about what that powder is actually made of, it's essentially this.
But it's the same
thing.
metal, yeah.
Yeah. It's just the actual particle size is different, and then ours is bound in that.
If ours is bound in a plastic
Yeah.
material.
So you can handle it with your bare hands. Like you can
Like,
load material.
This
Yeah,
is
exactly.
powder bound in plastic, and we're handling it.
Right.
It's fine.
It'd be a lot sadder if it was.
If it was
just
straight
a
up
pile
powder,
of
it's very sad. Couldn't pick it up.
Yeah. All right. So another question: what is the procedure if the sinter gas runs out during the process? So this is something that's interesting in terms of how you actually operate the sinter.
Yeah.
That's something that's going to be flagged before you actually make a sintering run. You'll know if you have enough gas for that run.
Yeah, so we actually have sensors set up to monitor pressure, and you can see, the furnace is smart enough to say, hey, I'm going to kick off a run, let me check that we have enough pressure to run this full run through. And if it doesn't, it'll actually warn you and tell you, hey, you can't keep this off, it's going to fail because you don't have enough gas.
Right. Let's see. What is the retort made of?
It's a refractory metal.
Cool. What is your max sintering temperature?
I believe on our sinter ones we spec up to highest temperature of 1300.
1300 C.
Yeah,
Celsius.
1300 Cs.
You have. Oh, you're talking about gas. Nice. You're getting some nice conversation happening in the comments.
Yeah.
Yeah, talking about gases. Cool. I know A2 and D2 are still beta materials, but what will the target as sintered hardness be?
So A2 we're actually hoping to have out pretty soon. Keep your eye out for an announcement.
Nice.
That A2 as a material itself, we can harden it basically like your wrought A2, so that's like high 50 Rockwells. So it's gonna be a higher hardness than H13. Expected to perform on the material side very similarly to your standard A2, heat treatable, pretty hard.
Cool. So you think as sintered, it's going to be pretty close to what you would see.
As sintered, it'll be a little softer.
Yeah.
You could definitely heat treat it to get a much higher hardness.
Right. And that's a good note. It's a question we get a lot is are your parts heat treatable? And the answer is yes.
Oh yeah.
They're just like a metal, any other metal part. You can heat treat them if you want to polish them. Once we start releasing steels that are a little more weldable, like 316L, you can weld them.
I mean, you can weld our 17.4.
You can weld 17.4 as well.
Yeah.
Yeah. So definitely yes, achieving the hardness is something you can do. Is it recommended to sinter parts that are the same or similar sizes? Would you avoid mixing sizes of parts to sinter? That's an interesting question.
Interesting. Not really. We've designed our sinter so that if you can fit it in the sinter, it should run successfully.
Yeah.
With our sinter 2, we're actually working on designing to make sure like large parts will succeed.
Great. How important is thermal uniformity in each part during binder removal and sintering? So we covered that a little bit. Very important. And it's important to make sure to keep your part dimensionally stable and also getting the mechanical properties that you want.
Right.
Can your furnace be used for heat treatment after sintering? That's a great question.
As of right now, you can't. It's we recommend you just take your part and heat treat with your cheaper small heat treat furnace.
Yeah.
The idea is you don't want to tie up your very expensive sintering oven doing a simple heat treat process that you can do on your standard box oven.
Yeah, exactly. It's you don't want to be taking up bandwidth or something that's you can be putting batches through. Exactly. Is binder removal more sensitive to thermal uniformity of sintering?
Binder removal so thermal uniformity during sintering during the actual sintering process is probably more critical when you're hitting that when you want to make sure your metal is uniformly heated when it's shrinking. During the binder removal, it's also important, but probably a little less so. You just want it to get consistently heated so that it removes all the polymers around the same time as we expect it to.
All right, yeah, so just making sure that all of them clear out.
Exactly.
Okay, cool. All right, so that's all the questions that are there now, but if you have more questions as we start to wrap stuff up, make sure you throw them in there so we can answer them before we wrap up, and because I think that is all that we have prepared. In the next few weeks, we're going to dive a little bit deeper into metal 3D printing applications. So we've talked a lot about the process the past few weeks. How do you print parts? What actually happens? Print, wash, then sinter, how the sintering oven works. So now we're going to dive deeper into, okay, we know how this machine works. What can you actually use it for? What are the advantages of actually having a Metal X system or a metal 3D printer in your shop? And so that's what we're going to dive into in the next few weeks. It looks like we got a couple more questions. How do you purge the vaporized binder polymer?
So we are running basically a gas, an inert gas through, and that purges out all the burnt out polymer parts.
You just blow really hard on the center and blow it out of there.
There's a continuous gas flow where, yeah.
All right. Cool. So it's like an exhaust sort of deal.
Yep.
Okay. This is a follow-up question from Michael. The most common refractory metal is molybdenum. I know of several others that are more exotic. I was wondering if your process required one of the more exotic refractory metals. I don't know if that's something you can answer.
I would not call it exotic, but I can't really tell you what it is.
All right, there we go. All right, so that looks like all of the questions we have. Thank you, everyone, for joining us this morning. And thanks to Michelle for joining us on the show.
Thanks for having me.
Yeah. Have a good weekend, everyone.